So now we're taking the same principle, and instead of just looking at the electric potential energy, we want to define a new term, electric potential. So this can be really confusing for introductory students because we're using language that's very similar. This is not potential energy, this is electric potential. Think of this also, if you want, as voltage. Okay? We're going to talk about we talk about this in more practical terms as the voltage. But here's the definition. The electric potential is the potential energy per unit charge. The electric potential is the electric potential energy per unit charge. So when many times you're not interested in a potential energy, you're interested in the change in potential energy. In fact, almost always you're interested in the change in potential energy, which is why you have to define a reference point for the potential energy. So many times it's the difference in potential between 2 points that we're interested in, and then that just becomes the difference in potential energy. So let's easiest way to think about this is to look at some examples. And so let's go back to the example that we started with at the beginning. In fact, I'm going to just borrow that nice little drawing we did of this parallel plate capacitor, and we'll refer to this down here. So if we look at this parallel plate capacitor, okay, we've got an electric field E, and again, we could write an expression for that electric field. This is the x direction, this is the y direction. Now, instead of moving the charge, though, I'm going to take this out. We did that to calculate the amount of work in moving the charge. Well, shoot. That's all right. I'll draw back in the electric field line here, and let's put a charge plus Q there. All right, so I've got this Q inside my electric field, and I want to think about the electric potential. Okay, so let's go ahead and calculate the electric potential energy here. Why not? If I want to know let's say I'm moving it from A to B. Okay, moving the charge from A to B. And it's going to end up there. All right. So the change in potential energy moving from A to B, which by the way would be UB minus UA, is going to be equal to the negative of the work done by the electric field. Work done by the electric field when we move from A to B. Okay, now, this electric field is, well, let me calculate. The work done by the electric force as we go from A to B is going to be the electric force dotted into dl, just like that. Now, the electric force, we know, is sigma over epsilon, and in the x hat direction. Now, in this case, I'm actually moving the charge along x hat dx, or dx x hat, yeah, that's right, dotted into x hat dx. And so the work done by the electric field as we move from A to B will just be sigma over epsilon naught. X hat dot x hat is 1, and it's the integral of dx, moving from, let's call it xa to xb. xa to xb. Why not? Which, that's easy. Sigma over epsilon naught delta x. Okay, cool. That is the work done by the electric force. Now let's think about that for a minute. The electric force is in the x direction. The motion of the charge is in the positive x direction. The electric force does positive work in moving the charge from point A to point B. Sounds great. Everything's cool. Delta x is positive because xb is greater than xa. So I've come up with a quantity here that is actually positive. So the change in potential energy would be the negative of the work done by the electric force in moving from A to B, which would be sigma over epsilon naught delta x. Remember, the sigma here is the surface charge density of the plates of this parallel plate capacitor. I could write it as Q over A. For now, I'm just going to leave it like that. And in fact, if you wanted to leave it really general, you could make it like this. It's the magnitude of the electric field times delta x. So this tells you some stuff. Okay, let's see. Now, I missed a negative sign here. Okay, so the negative of the magnitude of the electric field times delta x. That's the potential energy difference. And if we're interested in the voltage, then, okay, what we're saying here is that the change in potential energy would be equal to Q, and this is my same blue Q that I've drawn up here, times delta V. And so I'd be saying that the change in potential energy, their change in potential rather, delta V, is equal to minus E delta X over Q. All right, which is just the change in potential divided by change in potential per unit charge. Okay, so let's think about that now. Think back to our gravity analogy. This situation is like taking a ball and dropping it in a gravitational field, right? The gravitational field is doing positive work on the ball as it's going down. That ball experiences a decrease in potential energy, right? Yeah, a decrease in gravitational potential energy, because it starts at a high point, ends up at a low point. Now, here, the same thing is happening. The potential energy has decreased. See how we have the negative sign right here? And so the electric potential energy, I might even want to put an E right there to indicate this is electric potential energy, did in fact decrease with this negative sign there. All right. The electric potential has also decreased because I've got the E delta X, the Q is positive, all of these terms are positive, and so I have a change in electric potential that is also negative. Okay? So, what this tells us some things about this situation here, where we've got a change in potential energy that's negative because we've gone from well, think about it like this. If we have a positive charge near the positive plate of the capacitor, it's got a lot of force on it. And that force, that electric force, is going to want to push it to the other side, toward the negative side, right? And so it decreases the potential energy to move the charge further from the positive plate. All right? A decrease in potential energy. But it also lowers the voltage as the charge moves from the positive plate to the negative plate. Now remember that the voltage is the amount of potential energy per unit charge. And so the what that tells us is that the voltage is higher near a positively charged plate than it is near the negatively charged plate. So let's reverse the situation and do something a little bit different. Because we have a potential energy decrease. I'm going to write these down. U decreases and V decreases. Okay? So let's do a negative charge. Let's see what happens if we do a negative charge in here, okay? So same scenario here. But now we're going to change that to not be positive, but to be negative. Okay, so same thing, move a negative charge minus Q from A to B in the same the same parallel plate capacitor or steady electric field. Okay, so the potential energy difference will be the negative of the work done by the electric force. Now, let's think about that for just a minute. Because this electric force is, the electric field is the same, right? So, I missed something. Wow, I missed it badly. Oh, okay. Back up a minute. Here's where I missed it. Okay, let me back up here. I said the work done by the electric field is equal to the integral of F dl. That's right. But I skipped something. The force on the charge there is actually QE dot dl, and I forgot the Q everywhere. I don't believe that. Oh, that's a killer. But that little Q would appear in all of those things, okay? There's a Q there. And so then when I say that this is equal to Q, man, what a terrible mistake. But we caught it. We caught it. Okay, so what that did is that kills the Q here. Because then when I divide delta V, I already have the Q in place. And so, yeah, now that is correct. Delta V, let me rewrite it though. Delta V is equal to minus E delta X. Okay, the point about the potential decreasing and the potential energy decreasing is still the same, but I had forgotten that Q. That's a critical part of it because I didn't actually have the electric force. What I had here was the work per unit charge. That was work per unit charge. If I put the charge in there, then what I was actually computing here was the potential, not the work done by the electric force. Okay, so we caught that. I'll do it right here, and hopefully that will make things a little bit clearer for what we just did upstairs, up here. So the work done by the electric force, all right, now let's do this right, is going to be equal, I'm going to go and do it like this, minus Fe dot dl. Now the Fe, the electric force, is the same as it was before, which is Q times E dot dl. Now that little Q, that's this constant little Q here, so that can come out, minus Q integral E dot dl, again going from A to B. So for this parallel plate capacitor, the electric field is sigma over epsilon naught x hat. That's my E. Dot dl, which is dx x hat, like that. And so I compute the change in potential energy. Oops. Shoot, I messed up again. No, well, yeah, I did mess up again. Let's see, how do I fix this one, though? The Q is the same. But I want to indicate that it's negative. You see what I'm saying? So right here, when I put Q in, I didn't have any problems doing that up here. I mean, except I didn't do it. Because the Q should be positive. But here the Q is negative. And okay, so let me do it like this. This is minus Q0. We'll do it like that, minus Q0. So when I put this Q in there, I have to indicate that that is actually a negative charge. So it's minus Q0. That becomes plus Q0 there. Okay, now I think I'm all right. Q0, the sigma comes out, epsilon naught comes out, and then it's the integral of dx from xa to xb, which ends up being the change in potential energy. Change in electric potential energy is Q0 sigma over epsilon 0 delta x. All right, now notice that that potential energy change is opposite what we get here. There's a negative sign there, right? There's not a negative sign here. So what that says is that the potential energy of this system, as I've moved the negative charge from A to B, has increased. All right? Now, this is a little bit different than the gravitational setting. And the reason is we can't think about a negative mass. We can't, if we had a negative mass in a gravitational field, the idea would be that if we took a ball and held it above a surface, in a normal gravitational field, the ball drops. That's a positive mass. If we had a negative mass, that ball would actually go the opposite way. It would not fall, it would go up. So here, this is a negative electric charge, and it does not feel a force along the lines of the electric field. It feels the force against the lines of the electric field. So if this charge has moved from A to B, negative charge moved from A to B, there was an applied force that moved it. In other words, the electric force did not move it. And the work done by the electric field is negative for that negative charge. So the potential energy ends up being a positive value. We gain potential energy as the negative charge moves from A to B. But what about delta V? Well, delta V, remember, is equal to delta U divided by Q. Now the Q here is minus Q0, right? And so that takes that out, but look at what happened. We're left with a negative sign. And so the change in potential is still negative. That's interesting, okay? So potential energy increases, but the potential still decreases. And that tells you something. What it tells you is that the potential, the voltage, is independent of what kind of charge you have in your in the system. All right, whether I have a positive charge, a negative charge, it doesn't matter. The potential is a quantity that is completely independent of any test charge, whereas the potential energy does depend on the test charge. The potential energy increases because I've got a negative charge moving from A to B. If it was a positive charge moving from A to B, the potential energy decreases. But the potential decreases no matter whether I've got a positive charge or a negative charge. So what that means is the potential depends on the E field, but not on the test charge. E field, but not on the test charge. Okay? And then what that means is that I can draw surfaces or lines where the electric potential has the same value, and I can chart what are called equipotential lines or equipotential surfaces. Let's look at a different example. What about a point charge? We found out in the last video that the electric potential energy from a point charge is equal to KQQ over R, just over R, like that. So the potential energy, and by the way, this is, we can say minus U at reference, which is often put to 0. U reference goes to 0 as R goes to infinity, usually, okay, for a point charge. So what about the potential from a point charge? Well, this is going to be U over Q, which is just going to be KQ over R. And again, you can say minus V ref, because just like there's a reference point for potential energy, there's a reference point for voltage as well. And so, again, a lot of times that it's set to 0 as the charge is infinitely far away. But look at what that means. The potential is dependent on R. In fact, it's 1 over R. So let's say that I have a point charge here. And remember, we know the electric field from a point charge is radially outward. And we know an expression for that too. E is equal to KQ over R squared R hat. But if we look at the potential, it's KQ over R. There's no vector associated with it. It's a scalar quantity. But it depends on the radius, the distance away from the charge. And it has the same value for every point around, every point on that same R. And it decreases as we get further and further away from the charge, 1 over R. So these would be called lines of equipotential. Whereas these are lines of electric force, or electric field. Lines of electric field. So the lines of equipotential, by the way, the value of the electric field also only depends on R for a point charge. And so the electric field also has the same value everywhere around the charge, but it points radially outward. That's why we draw the arrows. These little lines of equipotential are just concentric circles around the charge. If you want to look at different types of equipotential surfaces, look at the book here. So there's the point charge, and it shows the isolated electric field lines. The potential is the same along equipotential line. Notice what that means. No work is required to move a charge around an equipotential surface. If you want to move a charge in a circle around a test charge, around an isolated point charge, you can do it with no work. It's just the same as saying the work is only done when the force is in the direction of the displacement. Because if I displace a charge around a point charge, that doesn't require any work. That's why charges can orbit other charges without doing any work, because the trajectory, the direction of the displacement is perpendicular to the lines of force that would be required. So what if I had a plus and a minus charge? Well, we looked at the electric field from that, and how remember the electric field lines connect the positive to the negative, right? Or connect the positive to infinity and the negative to infinity. But look at what happens with the equipotential lines there. Those equipotential lines are around the positive charges, around the negative charges, but they're positive, KQ over R, positive around the positive charge, and negative around the negative charge. So think about these equipotential lines like a topographical map, like they're hills, right? They're higher value, 1 over R, closer to the charge. They drop off as you go away. So around that positive charge, there's like a hill that comes up to the top of the positive charge. And around the negative charge is like a valley that goes downward. And the shape of that hill and valley tells you what will happen if you drop a positive test charge somewhere in that region. It'll follow the contours of the electric potential and roll down the hill, so to speak. There's the electric field and equipotential surface. Here's the equipotential surface here for two charges that have the same sign, say two negative charges. If they were two positive charges, the voltage isopotential lines would be positive. And so again, those isopotential lines, a charge doesn't require any work to move around those lines. And there's what I was talking about the topographical map. You can see how you have a hill around a positive charge and a valley around a negative charge. And that's what that kind of looks like if you look at the map from top down. Parallel plate capacitor, what you see, so you see the electric field lines, and notice that inside the parallel plate capacitor, the lines of equipotential are straight lines. they're perpendicular to the electric field lines. By the way, equipotential lines are always perpendicular to the electric field lines. Even up here, you see that. Every time you see an equipotential line, you see that it's perpendicular to an electric field line. That's always the case. There's some fringing fields out at the edge of the parallel plate capacitor. But you can also see how the voltage starts at the positive plate. It's high, 100 volts, and it drops off evenly as you go across that parallel plate capacitor. So one of the formulas that you see for potential, maybe that's back over here. I just want to point this out because this is a common mistake that introductory students make. They give you a nice little formula. Oh, here. Okay, so in this parallel plate capacitor, this is very similar to the calculation we did already. The work done is minus delta U, which is minus Q delta V. The change in potential is V from A to B. And so the work is Q times V from A to B. When you calculate that work, ED, that D is the same delta X that we used, and so you have QED equals VAB. So V, the potential between 2 points in a uniform electric field, that would be like between the plates of a parallel plate capacitor, is equal to E times D. So E is equal to V over D, but that's only true for a uniform electric field like you have between the plates of a parallel plate capacitor. That is not true for an isolated point charge. In fact, the situation is more like that. You have to integrate, and that's where you get the V equals KQ over R. So just keep in mind the different expressions for voltage potential from a point charge and from a uniform electric field. Let's see, there was one more thing I saw up here. Oh, energy. So we've been talking about the potential energy in these situations. So you can also then, if you can talk about potential energy, we can talk about kinetic energy, right? So if the potential energy decreases, let's say that you have a positive, a parallel plate capacitor, okay? Positive charges over here, negative charges over here. And so your electric field looks like this. Let's say you have a positive test charge that moves this way, all right? So that's a potential energy decrease. It decreases in potential energy. Well, where does that potential energy go? Kinetic energy. Kinetic energy increases. And so if the potential energy decreases by an amount that you can say is equal to, let's see, what did we have up here? We calculated it. Q times delta V, right? Q times delta V. Well, the kinetic energy increases. Maybe it starts at rest, or maybe it doesn't. Then it would be like that. Conservation of energy. Change in potential energy, delta U plus delta K has to equal 0, or equals the work done by non-conservative forces, right? And so this is a nice little way sometimes to calculate the velocity of a charge once it comes out of an electric field. And those are things you can do with that. So there's a section on calculating electric potential and determining field from potential. So one more video for this chapter should do it.